In this video, we're going to apply F-Bell's principle, the Pauli exclusion principle, and Hun rule to write electron configurations using noble gas configuration. So just to recap on how to write electron configuration. So you learned the electron configuration notation, which has our principal quantum number, which is our n, our orbital or block number or sublevels, and our exponent that tells us what position the block is in. We also went over F-Bell's principle, and we used that principle to write different electron configurations for elements. The problem is that sometimes these electron configurations, as you noticed, can be super long and tiring to write. And you are probably asking yourself, is there a better way? And the answer to that is yes, there is. And that is what we're going to go over in this video today. The easier way is our noble gas configuration, also known as like the shorthand method to writing electron configurations. The noble gas configuration takes into account the closest noble gas before the element. So if you are looking at a periodic table, the noble gases are in the very last column on the periodic table, known as column 18. Okay, all of these elements right here, they are known as noble gases. When writing electron configuration using the shorthand notation, you need to remember a couple steps. So if we wanted to write an electron configuration for aluminum using our noble gas configuration, the first step is to find the closest noble gas before the element. So if you take a look at aluminum, aluminum is here. You're going to go backwards, and you can see that the numbers are decreasing as we're going backwards. The first noble gas that we are going to hit before aluminum is neon. So you're going to take neon, and the second step is to write neon in brackets. Okay, so we have the symbol for neon. We are writing it in brackets. And what this does is this noble gas is like a placeholder for our electron configuration. So after the noble gas, we start writing the configuration after the noble gas. So if neon is here, we will start our configuration right over here at this row. And this is principal quantum number 3. We are in the S block. We are passing 2 elements in order to get to aluminum. Once we get to aluminum, we are in still row 3, but we are in the P block now, and aluminum's position is number 1. So this is the full noble gas configuration for aluminum, and it's definitely much easier than the longhand notation. So now that you know the steps in writing a noble gas configuration, let's do a couple practice problems. So example problem number 1 says, what is the noble gas configuration for iron? So if iron is over here, the noble gas before the element is going to be argon. We're going to take argon and put that into brackets, and we're going to start our configuration after argon, and that is our 4s2. And then if you remember, for the D block, the rule is n-1, so we are in 3D, and iron's position is 1, 2, 3, 4, 5, 6. So that's how we get 3d6. The next example is for bromine. Bromine is right over here. The closest noble gas after bromine, if we go backwards, is argon. We take argon, we put it in brackets, and we start our noble gas after argon. And so if we start over here, we are in principal energy level 4. We pass the S block. We are into the D block now, n-1, so we write 3d10. Pass all of these elements, we get into the P block, 4p5, and bromine's position, like I said, is 5. 1, 2, 3, 4, 5. So this is the full noble gas configuration for bromine. Our next example is for element 64 in the F block. So if we take a look, our F block, the asterisk is right over here, the first row. So the closest noble gas to that is going to be xenon. You take xenon, you put it in brackets, and you start the configuration after xenon. So we have 6s2, and now we are into the P block, which we remember it's n-2. And so it's 1, 2, 3, 4, 5, 6, 7, 8. So 4f8. The last example is for radon, which is a noble gas. So how do we write a noble gas configuration for something that is a noble gas? You still have to find the closest noble gas before the element. And in this case, we're going to go backwards, and that's going to be xenon. And we start our electron configuration right over here. So 6s2, 4f14, come back over here, 5d10, into the p block, 6p6 is the full electron configuration for radon. The last thing that we're going to discuss in this video is valence electrons. The definition for valence electrons are the electrons that are on the outermost shell. So if you're taking a look at electron configuration, this is for aluminum, to find the electron configurations for atoms using electron configuration, you add together the exponents of the outermost shell. So those are the principal quantum numbers that are the highest. And if you notice over here, we have a 3s2 and a 3p1. So because 3 is the highest principal quantum number, that is the outermost shell, all we need to do is just add the electrons together of the exponent. So 2 plus 1 is going to be 3. And that means aluminum has 3 valence electrons. These are our noble gas configurations for the examples 1 through 4 that we did in this video. Can you pause the video now and count the number of valence electrons for each of these elements? So hopefully you got your answers correct and you were looking for the highest principal quantum numbers inside of all of these noble gas configurations. You would notice that for iron, iron has 2 valence electrons. Bromine has the highest principal quantum number is 4, so 5 plus 2 is 7, so 7 valence electrons. Gadolinium, we have the highest principal quantum number, which is 6, so this is going to have 2 valence electrons. And lastly, radon, the highest principal quantum number is 6, so the exponents for that, 6 plus 2, is going to give us 8 valence electrons. And that concludes our video for today. Thank you for watching.